Welcome. As we know from earlier classes and as we have already seen in the review, there are three kinds of systems: isolated systems, closed systems and open systems. We say that isolated system is something that does not exchange either mass or energy with its environment. A closed system is something that can exchange only energy with its environment but not mass, whereas open systems can exchange both mass and energy with its surroundings or environment. We saw that isolated system was a good concept, and this far in this module 2 we have looked at closed systems. Now let us start looking at open systems. To make things simple, let us begin with one input stream and one output stream. We will derive this, we will derive the relevant expressions for one input stream and one output stream for a particular system, and then generalize it for many input streams and many output streams. Also, let us call the rate of heat interaction across the system boundary. As we have seen, this heat interaction and work interaction makes sense only when they cross the system boundary. The rate of heat interaction across the system boundary, let us denote that by q dot. Brings in the rate aspect, the time rate, and the rate of work interaction across the system boundary is w dot. This is our terminology. So if we use this to represent our system, so this is a system which could be anything, which could cover very many real life parts, real life aspects of a plant, bioprocess plant, or it could be even a conceptual one. We said we will consider one input stream and one output stream, and this is our heat interaction here, and this is our work interaction which cross the system boundaries. And as we all know, there is a convention to be followed, and the convention that we are following in this course is that the Q, the heat interaction into the system, is positive and the work interaction out of the system is positive. So as written, both these are positive. Now let us write an energy balance. We had written mass balances earlier. Now let us write an energy balance. Unlike mass, energy can neither be created nor destroyed, that we all know, or in other words it cannot be generated or consumed. Therefore the generation and consumption terms need not be taken into account whenever we consider energy. The energy balance, written in terms of rates of accumulation, input and output, those are the other three remaining terms in a balance apart from the generation or consumption, can be written as this: d dt of the energy of the system, note that is the energy of the system, the total energy of the system, equals the rate of energy input into the system, EI dot, minus the rate of energy output from the system, EO dot. It is quite intuitive, straightforward to see. There are no other terms that can be included in this. If you want to think about it, please go ahead and do that. You will realize that there are no other terms that can be included in this. It is very fundamental, simple balance. See, all these balances are just like accounting in finance, where you have a credit, a debit and a balance. So where you put in these is what makes the difference. It is as simple as that. So we have an energy credit and an energy debit and the balance. Let us call this equation 260. If you look at the input rates for the system under consideration, let us take a look again at the system under consideration. The energy input could be due to the stream itself and the heat interaction in the system that we have written, which we have started to consider. That is, it has one input stream, one output stream, and energy interaction of heat interaction of Q and a work interaction of W, or the rates of that as Q dot and W dot. Therefore, the input rate is due to the streams and the heat interaction. Similarly, as we have seen in that figure, the output rate could be due to the streams itself, there is the energy that is carried by the streams and the work interaction. If you think about it, this heat interaction and work interaction can be accounted for in any place. You could account it for in the input, you could account it for in the output, as long as you choose your signs appropriately. Let us not get into that. We will take the intuitive route and we will account for the heat interaction in the input rate, the rate of heat interaction in the input rate, and the rate of work interaction in the output rate. It is kind of intuitive in the way we have written our system. If you take this into account, we can write equation 260 that we have seen here, simple energy balance, as d dt of E of the system, same as here, equals, we are explicitly showing the various contributions to EI dot. It could be E dot of the inlet stream and Q dot, okay, plus Q dot, and similarly minus this EO dot term consisting of E dot of the outlet streams, outlet stream in this case, and W dot. Let us call this equation 261. Now, it is convenient to consider two kinds of work. We have already let us assume that the other kinds of work do not exist and only these two kinds of work exist. One is shaft work, WS. You can go back to your early days of thermodynamics, you would have learnt it there, shaft work, and PV work, work due to pressure, volume expansion, and so on. Let us consider that these are the only two work interactions. If there are other work interactions, you just have to add them to this, it is quite simple, we can do that later also. For development, let us consider only these two work interactions. If we do that, then the W dot term can be written as Ws dot, which is the rate of shaft work, plus the rate of PV work that is going out minus the rate of PV work that is coming in. Note that this is PO VO hat, this is the mass specific volume of the streams, and you know that P naught V naught, you can work out the units here. If you multiply it by the mass flow rate of the outlet stream, you get the rate of work interaction that crosses the system boundary due to PV work. Similarly, this is the rate of work interaction that crosses the system boundary into the system through the inlet streams. We will call this equation 262. As we have already, let me state this again, m dot is the mass flow rate of the streams and V hat is the volume per unit mass. It is nice to have this in a complete form here, first time we are kind of introducing these things. Now, this equation 261 that we just wrote can be written as d dt of E of system, the accumulation term, equals E of the rate of E of the inlet streams plus Q dot minus E dot of the outlet streams. All this is from earlier. The only thing that we are doing here is expanding the W dot in terms of the shaft work interaction as well as the PV work interaction. So, plus Ws dot plus MO dot PO VO hat minus MI dot PI VI hat. Now, if you transpose this, subtract terms, or in our standard way, if you take terms to one side and so on, E dot of the outlet stream minus E dot of the inlet stream, there is a minus here, there is a plus here, therefore, it is actually a minus. You have a plus MO dot PO VO hat and this is minus minus is a plus here, on the other side minus mi dot pi vi hat plus d dt of E of system equals whatever remains here q dot minus ws dot. Okay. We will call this equation 263. Now, let us look at E in a little more detail. This E is the energy of the system that can consist of internal energy, kinetic energy, potential energy, surface energy, electrical energy, and so many other energies it could. And using the regular expression for energies, and okay, let us see whether we are generalizing it here. This equation 263 can be written as, it is reasonably general here, mo dot internal energy plus kinetic energy, which is half u o squared mo dot, that is a rate here, that is why you have a dot here, plus the potential energy term g z o mo dot, plus whatever terms that you want to put in for the other energies, plus the PV work mo dot po vo hat, this is for the outlet stream, minus mi dot ui internal energy hat, specific internal energy, multiplying it by the mass flow rate here. Therefore, you need a specific value here ui hat plus half ui squared, this is the kinetic energy term, plus g z I, the potential energy term for the inlet stream, plus the other terms corresponding to the other energies, plus the PV work term pi vi hat. This equals plus d E of the system dt equals q dot minus ws dot. Essentially, we have expanded the E of the outlet streams and the E of the inlet streams, and then put in the various terms together. We will call this equation 263. Now, since enthalpy equals u plus PV, there is a need to bring in enthalpy here because the enthalpy values are probably easily available. Enthalpy equals u plus PV. This equation 264, if you look at 264, you have u o hat plus po vo hat. Therefore, you have an enthalpy term right here by the combination of this, and enthalpy values are probably more easily available. Excuse me. Therefore, let us combine them and write this as mo dot times ho hat, enthalpy of the outlet stream, the specific enthalpy of the outlet stream, plus the kinetic energy term half u o squared, plus the potential energy term plus g o into mo dot, plus the terms that correspond to the other energies, minus the corresponding things for the input stream mi dot into hi hat plus half ui squared plus g z I plus the other terms, plus d dt of the E of the system equals q dot minus ws dot. Let us call this equation 265. Now, if the mass flow rates of the input and output streams are the same, they are typically the same, otherwise there will be accumulation. Mathematically, mo dot equals mi dot, and let us call that by a simple m dot after dropping the subscripts because they are the same. If that is the case, and we indicate output minus input by the delta, you see there is an output here, there is an input here, there is a minus here. If you can indicate that by the delta, then we can write m dot take out, then ho hat minus hi hat, that becomes delta h hat, plus half of UO squared minus UI squared, that becomes delta U squared, plus G of ZO minus ZI, which becomes G times delta Z, and hopefully you can write the other terms in terms of the differences. So that is indicated by the dot dot dot. This is for the terms that correspond to the other energies, plus the remaining terms d dt of the E of system equals q dot minus Ws dot. We will call this equation 266. So this is in a form that we can directly use. If you know the differences in velocity between the inlet and outlet, the differences in heights between this is outlet and inlet, this is also outlet and inlet, and the differences in enthalpies of the stream at the outlet and at the inlet, then this can be computed if you know the energy interaction, the heat interaction, and the shaft work interaction. So this is a nice form of the energy balance, a very useful form of the energy balance. Note that we considered only one input stream and one output stream for this particular system. Now if we generalize things, we have it of the form that can be easily generalized. Generalization, if there are multiple streams, for example if there are C input streams and D output streams, the energy balance is nothing but you sum over all the output streams and sum over all the input streams and subtract one from the other. Energy is a scalar, it can be subtracted. Therefore sum over D output streams of mj dot, this j is the index for the outlet streams, mj dot times hj hat plus half uj squared plus gzj plus the terms that correspond to the other energies of these streams, minus sum over C inlet streams or input streams, the k is the index for the input streams, mk dot times hk hat plus half uk squared plus gzk plus the terms that correspond to the specific energies of the streams, other specific energies of the streams, plus d dt of E of the system equals q dot minus Ws dot. So now we have a nice general equation that can be applied to any open system that exchanges mass and energy with its surroundings. I think there is an equation number, equation number 267. So this is a nice equation to remember. As usual, we would look at how to apply this equation to get more familiar and also to develop the higher level skill of application. Let us take a typical example and apply the energy balance to that. Steam is used for various purposes in the bioprocess industry, as we all know. Steam is the one that is used to sterilize the central part of the bioprocess, which is a bioreactor. As you all know, sterilization is essentially to create an environment where there is no microorganism, and then we add the microorganism of interest to us so that only that microorganism grows. Otherwise, as we know, there are so many microorganisms present in the air all the time, and if we do not sterilize, if we do not eliminate all of them, then whatever is available in the air will grow along with the organism of interest. There would be competition for the food that is available, which may not be desirable for the optimal production of the product, and therefore we sterilize things, we make sure that we have a clean slate when we start out with, and under sterile conditions we add the microorganism of interest into the bioreactor and then let that organism grow and produce the product of interest. For sterilization, steam is used, slightly higher pressure steam and at temperatures of about 120 degrees, 121 degrees are used. Also steam is used for heating the various liquid streams. sometimes the bioreactor needs to be maintained at temperatures of 37 degrees C, maybe even 30 degrees C when the outside is about 27, 28, maybe in the colder months in some parts of India, maybe standard in some other parts of India. Therefore, we need to heat the streams to get to the optimum temperature at which the bioreactors work. So, to do that, there are heat exchangers that are used to heat up these streams, and the heat exchangers predominantly use steam. To read out from here in a formal fashion, heating of liquid streams and the bioreactor to the needed temperature, say 30 to 37 degrees C, and in situ sterilization of bioreactors, these are the two things that we talked about now, are some examples of steam use in the bioprocess industry. So, we need to get comfortable with steam. The thermodynamic properties of steam under various conditions, condensed, which is also the liquid, this we need not worry about too much. Typically, we need to look at saturated or superheated. What does saturated mean? Recall the phase diagrams that we reviewed in the first module. We had a PT diagram, pressure versus temperature diagram, and there we had the fusion line, the vaporization line. Let us focus on the vaporization line. The points on the vaporization line correspond to saturated conditions, and if steam is in that state, it is called saturated steam. And or if you look at a PV diagram, we pressure versus specific volume, we had a dome, and the conditions inside the dome correspond to the saturated conditions. And superheated, of course, we know it is completely a vapor. Therefore, these two are the ones that are usually of interest to us. The thermodynamic properties of steam under various conditions, saturated or superheated, are available in steam tables, and a copy of the steam tables is available as an appendix of your suggested textbooks, Smith, Vannes and Abbott. Please take a look at that appendix and familiarize yourself with the various values that are given there as functions of pressure, temperature, or maybe one variable. Why don't you take about 5 minutes to familiarize yourself with these steam tables. Go ahead, please go to the appendix and take a look at these two tables, the saturated tables and the superheated tables of steam. Now that you are familiar with the steam tables, how it looks like, what are the various values there and so on. For the above uses, the generated steam that is available at 100 kilopascals in a saturated condition is compressed to 300 kilopascals using an equipment called a compressor. You might have already heard of a compressor. Compressor essentially does compression, increases the pressure. Here it has gone from 100 kilopascals to 300 kilopascals. The compressor, the equipment, when well designed, can be approximated to work under adiabatic conditions, which means it can be assumed that there is no heat interaction between the compressor and the surroundings. Also, such compressors do not have much difference in the entry and exit elevations. Okay, ZO, ZI and ZO, there is not much of a difference. The pipes are also so sized to equalize entry and exit velocities. Therefore, UO, the small UO equals the small UI. The compressor efficiency, that is defined as the maximum or the isentropic work to the actual work, is 0.8, and what we are expected to do here in this exercise is to estimate the work needed to operate the compressor per kg of steam compressed for steady state operation. This is a very typical calculation that is done, the work that is needed to operate the compressor per kg of steam compressed, or work that is needed to operate the compressor itself, translates directly to the energy costs that are required for the compressor. Some compressors are huge energy guzzlers, so it is good to have an idea of the energy that goes into compressor operation. So thermodynamic application of thermodynamic principles is going to tell us that, especially the final equation that we derived for open systems is going to tell us that. Let me start you out with the solution, and then probably you can take about some time to work it out, then I will give you the final solution. The thermodynamic properties of steam can be obtained from the steam tables. For saturated steam, note you need to look at the saturated steam tables, either on the line for on the PT diagram or under the dome for the PV diagram. You need to have this idea in mind when you look at steam tables. For saturated steam at 100 kilopascals, which is the inlet conditions, the enthalpy values are given in the table for the 100 kilopascal condition. That turns out to be 2675.4 kilojoules per kilogram. This was the specific value per mass value, and the specific entropy is 7.3598 kilojoules per kilogram per Kelvin. So this is some data for you to start out with. Take a look at the equation that we have developed and see what values can be obtained from the steam tables, substitute the values and get the final solution. Maybe some help might be required towards the final solution in terms of how to get the work done and so on. We will come to that. At least look at the steam tables now and substitute the values that are available there into the energy balance expression. Go ahead, take about 10 minutes. Okay, let us move forward. If an isentropic compression is considered, and this is the limiting value, we know in an isentropic process the entropy remains constant. Okay. So we will make use of that point. Therefore the entropy at the outlet must be the same as the entropy at the inlet. Therefore we have a value for the entropy at the outlet as the same 7.3598 kilojoules per kilogram per Kelvin as at the inlet. Now by interpolation in the steam tables, we are going to linearly interpolate. This happens to be in between the values that are given in the steam tables, and therefore we will assume in that narrow range the variation of the values of enthalpy and entropy are going to be linear. And therefore if we interpolate, in other words you take the value above 300, below 300, take the entropy value, in this case enthalpy values, and then for this much amount of a change in temperature you have this much amount of a change in entropy or enthalpy in this case. Therefore for the difference that corresponds to 300 kilopascals from its previous value, what would be the change in enthalpy that needs to be added to the value that is before or below 300 kilopascals. That is the way we need to go about it. Please do that. If you have any difficulty you can always clarify later. So we linearly interpolate to get the value, and for 300 kilopascals we need to look at superheated conditions. It is no longer saturated and we need to look at superheated conditions. In that case by interpolation we get the enthalpy of the outlet stream as 288.4 kilojoules per kilogram, 2888.4 kilojoules per kilogram. Therefore the change in enthalpy for an isentropic process is the outlet minus the inlet value, that turns out to be 213 kilojoules per kilogram. Now application of equation 266 to our system, we need to very clearly identify what our system is, as we have said earlier also when we reviewed. If we do not identify a system clearly, then it could be a mess. The application of balances to one system at one time, the other system at other time in the same problem can lead to a lot of confusion. If applying equation 266 to a system which happens to be the compressor is chosen as a system, with the realization that delta U squared equals 0, because the condition given is that equal velocity of entry and exit streams. If you recall the problem statement, it said that the pipes are sized such that there is no velocity difference between the inlet and outlet, and also this delta Z or G delta Z equals 0, because the Z2 or ZO equals Zi, no appreciable difference in the elevations of the entry and exit streams. This was given, therefore we can take this term to be equal to 0, and since it is a steady state process, this term automatically goes to 0. d dt of any quantity in a steady state process can be taken to be 0. That is the definition of a steady state process. There is no variation with time at a particular point. All time derivatives are 0, and q dot equals 0 because the compressor works adiabatically. There is no heat exchange between the compressor and its surroundings. Therefore, q dot equals 0. Now, there are so many 0 terms. If you cancel out all those terms, what will remain of the balance is m dot times delta H hat. The kinetic energy term has gone to 0, potential energy term has gone to 0. We are assuming no other energies in the streams, and d dt of E system has gone to 0, q dot has gone to 0. So, the only thing that remains on the right hand side is minus Ws dot. So, m dot into delta H hat equals minus Ws dot. We will call this equation 268. Now, if we divide both sides of the above equation by m dot, we get delta H hat, this is minus Ws dot, note, and if we divide it by the m dot, we automatically get minus Ws, the rate part goes away. This is per unit mass, of course, you need to recognize that this is shaft work per unit mass. Let us call that equation 269. The compressor efficiency, which was defined as the rate of isentropic work, the maximum work possible to the actual work, this is the efficiency, compressor efficiency definition that we saw in the problem statement, can therefore be expressed in terms of the enthalpies, that is delta H isentropic, delta H hat isentropic to delta H hat, and as we know that these values we can get from the steam tables, we got those values already. So, let us substitute that. We know delta H isentropic for our case, we can find delta H, and therefore, the work requirement. Delta H, by transposing this equation, turns out to be delta H hat isentropic divided by eta, the efficiency of the compressor, that is given as 0.8, and delta H isentropic hat we have already calculated as 213. Therefore, 213 by 0.8 turns out to be 266.3 kilojoules per kilogram. This is delta H hat, and from equation 269 we have already seen that the shaft work required Ws was that is shaft work per unit mass is minus delta H hat, which is minus 266.3 kilojoules per kilogram. You might wonder about this minus here, why are we even looking at this minus here, what sense does it make? That minus comes in because of our convention. Note that negative sign indicates that work is done on the system, which makes sense, work needs to be done on the compressor for it to work, and therefore, this minus just indicates that work is done on the system. We do not have to worry about that anymore. our convention has been that the work done by the system is positive, therefore work done on the system is negative, that is all this indicates. Therefore, an amount of 266.3 kilojoules per kilogram of steam work needs to be done on the compressor. With this we complete module 2. In the next class we will begin with module 3.